this is what we were talking about last time. There was just a couple more things I wanted to say to finish up this discussion, and then move on to something else. So remember, this is kind of a busy diagram at this point, but when we're talking about numbers in Disco, Disco has four types of numbers. Right? There's natural numbers. We'll do 0, 1, 2, 3. We can only do addition and multiplication. If we want to add the ability to subtract, we get integers, negative numbers. Right? Or we could add the ability to divide, and we get fractional numbers, fractions. And if we want to do both, we get irrational numbers. Positive and negative things. And then I think the thing that we were talking about right at the end, we were talking about, other ways to move between these. So you can always go up automatically. Like Disco, anywhere, if it's expecting an integer and you give it a natural, Disco is fine with that. You can always go up. If you want to kind of go down, if you have a rational but you want something else, or there's a few different ways you can do it. So the absolute value function we mentioned will so actually if I switch over so if I say -5, what type is that? It says that's an integer. But if I say the absolute value of 5, what type is that? It says that's a natural number. Okay. So because it can't be negative, so it knows that. Also, if you say like -5/3, it says, well, that's a rational cube. But if I take the absolute value of it, it's not a natural number, of course, but it's a fractional, right? So that's one way. And then that's kind of to get rid of negatives. To get rid of fractions, one thing you can do is rounding. So there's two functions called floor and ceiling. So floor always rounds down. Well, yes, it rounds down. So let's see how that works. And ceiling rounds up, of course. So for example, if I say floor of 2/3, well, if you round 2/3 down to the nearest integer, you get 0. Right. And also, if I ask for the type of 2/3, that's fractional, but if I say, what's the type of, if I do floor, that's a natural. Or if I do floor of 17/3, well, I don't know, I guess it's 5, right? 15/3 would be 5. So that's fine. What about -1/3? Anyone want to guess what that is going to be? Matthew? 0. You think it's going to be 0? Dora? You think it's going to be -1? I agree, those are the only two reasonable options. It turns out it is -1. So it always rounds down, not towards 0. So just think of, you're on the number, or if you think of a number line, like it always rounds to the left. It turns out this is much more mathematically elegant and consistent, just like floor just always shifts things this way on the number line, not going towards 0. There might be some, it's quite possible that, like, for example, Java or Python, do something different. They round towards 0 instead of down, but anyway. It's kind of like rounding towards 0 is maybe kind of more practical in some sense if you're just thinking about kind of what makes sense to people, what they might expect to happen. But if you're worried about it like working out nicely mathematically, so you don't have to have weird special cases, it turns out doing something like this makes more sense. So ceiling, of course, just does the opposite, right? So ceiling always rounds up. So ceiling of 2/3 is 1. Ceiling of negative 1/3 is 0. Okay. And then the one other thing I wanted to point out, so it's a pretty common thing, like, let's say you have, 21, you have 25 pieces of candy, and you have 3 friends, and you want to divide the candy. Obviously, 25 is not a multiple of 3, but you're like, well, we'll have some left over, but like, how many whole pieces of candy can everyone get? Right? So if I want to divide, right, 25 divided by 3, but that won't be a whole number, right? That will give me like a precise answer. So I would want to do something like floor of 25 divided by 3, right? And say, okay, do 25 divided by 3, but then round down, and that'll give me kind of the, right, this is the quotient. Like if when you did long division in school and you write 25 divided by 3 is like, something, remainder, whatever, right? This is the quotient part without the remainder. And this is such a common thing to do that this code actually defines a special operator that does that. So if you do a double slash, that does like integer division, where you round the answer down. And so it's the same answer. If you know Python, Python actually has exactly the same operator that does the same thing. Anyway, just wanted to point that out. Any questions so far? And I don't remember if I showed this before or not, but like, maybe I did. This code is doing a lot of work behind the scenes to kind of figure out what type to make things so that everything makes sense. So for example, if I make a set with 1 and 2 in it, and I ask what's the type of that, it says, well, that's a set of natural numbers. But if I say, if it has 1 and negative 2, then it's like, well, it can't be a set of natural numbers anymore, because negative 2 is not a natural number. But it could be integers. And 1 counts as an integer, that's fine, if every natural number is an integer. So I can say, sure, it's a set of integers. But, or if I said like 1 and 2/3, it's like, yeah, that's a set of fractionals. The interesting thing is, right, if I say something like this, right, what type do you think this is going to have? Yeah, a set of Q, set of rational numbers. Yeah, so even though individually, right, this could be a natural number by itself, this is an integer, and this is like a positive fraction, so it could just be a fractional. But if you put them all in a set, they all have to have the same type, right? All the elements of a set have to have the same type. And so it says, well, the only type that can possibly work, that they can all have, is Q. So it's sort of, it's doing some work to figure that out. You don't have to worry about that. Cool. Is there anything else to say about this? I don't think so. And hopefully you all saw my email. I think someone asked about writing fancy symbols, and so I made a page of documentation. If you want to use fancy symbols, you're welcome to. All right. So I want to talk. The main thing I want to talk about today is functions. But functions in Disco. So we already. So we've seen how to define functions. Where you say the name of the function, you say colon, whatever type it is, and you define it. There's actually a lot more to say though, because in Disco, functions are what are called first-class values. And what that means is some languages kind of make a distinction between, well, there's values, there's things like ints, booleans, and characters, pairs, things like that. But then there's functions, and functions are like a totally separate thing. But in Disco, functions are values just as much as, say, integers are. So that means, what does that mean? Well, what kind of things can you do with an integer? Anything you can do with an integer, some things are like very specific integers, like adding. Okay, I can add integers, that's because of their integerness. But otherwise, like things you can do with integer, you can also do with a function. So for example, one thing I can do with an integer is give it to a function as an input. So apparently, in Disco, it's possible to have functions that take other functions as input. Because a function is just a certain kind of value, just like an integer is. So I could give it as an input to a function. Or when we learn more about, or like I could have a set of functions. We totally do that. We could return a function as output from a function. It gets a little mind-bending, but it turns out to be really useful. So, functions are first-class values. That means we can give functions as inputs to other functions, or return them as output, or a set of functions. Let's actually, just to illustrate that, let's make a set of functions, just to play with it. So, go back over here, or no, I'll do it here. So, let's say I'm going to make it's going to be a set of functions. Let's say, what kind of functions do we want in our set? Make them functions from natural numbers to I'm going to make it really simple. A set of functions from booleans to booleans. So let's make a few functions from booleans to booleans. So this function says, I don't care what my input is, I'm going to return true. Okay, and then I'll call this D2. D2 is the function that says, well, if you give me true as input, then I'm going to output false. And if you give me false as input, I'm going to output true. So then I can make my set, and I can say B1. Actually, you know what? I'm second guessing myself. I'm not sure if this will work or not. Let's try it. So, well, okay. could say, I wonder if I can say this. Um, F true. Okay, so I want to say, let's look at each function in this set of functions, and for each one I'm going to call it untrue, and that'll give me a boolean, right? And yeah, it doesn't like this either. Okay, so never mind. I'm going to have to figure out what's going on there. In theory, we could do this. Maybe right now it doesn't work. And okay, well, forget about that. However, there's other stuff about like giving functions as arguments to other functions. Like that stuff we can definitely do. So, so let's see. I'm going to make a function called. Actually, here I know what to do. Let's make. So remember on one of the modules, there was it says, well, you can the composition of two functions is defined in a certain way, and it asks you to prove something about it, right? So, like G composed F is the function that. So like compose F a function of G of F of X, basically. Okay. So the point is, I defined that notation, but if we can give functions as arguments to other functions and so on, like we can just define composition as a function, right? Function composition is a function that takes two functions and gives us a new function and putting them together. Okay. So how would we write that? Well, so I could give it some very specific type, like well, it takes a function from naturals to rationals and something, but that's annoying because it works the same way no matter what type of functions you give it. So I think we've seen this before. I can just like if I use letters, it's like those letters could stand for any type. Actually, it doesn't have to be just letters, like any name. So I'm going to say, all right, it's going to take a function from B to C and a function from A to B. And this is just like, making a pair. It's a pair of functions. And then it's going to return a function from A to C. Does this make sense so far, what we're trying to do? Again, we're making a function that takes a pair of functions as input, and it's going to give us a new function as output. So let's try to write this. We're going to get stuck, and I'll have to teach you something, one more other thing we're going to need in order to write this. So, well, compose, it takes a pair as input, so I can say, I can just call it like, G and F equals. So I have, G is my function from B to C, F is my function from A to B, and I need to output a function from A to C. But how do I just make a function here? The problem is that, if I have something, I have to somehow define a function that uses G and F. But so far the only way we know how to define a function is to actually declare it like this and give it a name. But I can't just declare something with a type and a name right in the middle of some other definition. So there's actually a way to create so-called anonymous functions. So I'll write here what we're going to do, and then I'll kind of talk through how it works. So I can say, for example, backslash is used to make an anonymous function. And okay, so what does this mean? The backslash we pronounce the backslash lambda, and you can actually write it using a Greek letter lambda. That's kind of a standard notation for this. So you can pronounce this lambda x dot. Okay, and what does it mean? Well, it means we're making a function that's going to take as input something called x. And then there's a dot. The dot just kind of shows you where that ends and where the output of the function starts. And then says, and this is what it's going to give as output. So, in general, something like if I write lambda x dot t, or I'll say lambda in dot out, is a function which takes in as input and gives out as output. Okay, so for example, if I say like lambda x dot x plus 1, right, this is the function which takes input x and outputs 1 more than x, right? But the point is, I didn't have to give it a name. I just say, it doesn't have a name, it just is this function. And it's especially useful if I'm like returning a function from another function. I don't really need to give it a name. I can just say, yeah, just the function I want is this one, the one that does this. And we can, let's try this. So if I switch back over. So we can also try, we can say like, okay, lambda x dot x plus 1. Well, I can ask for the type of that. And it says, yeah, that's a function that takes natural numbers and returns natural numbers. That makes sense? So I should be able to, for example, I could apply it to an input, 3. And it says that's 4. Okay? This is just like if I had defined some function f that added 1, I could say f3, it would say 4. Well, I didn't give it a name. I'm just literally writing down what function I want, and then I'm applying it to an input. So, going back to this, right? The definition of compose says, well, I'm taking in a pair of functions, g and f, and I need to output a function. The function I want is the function which takes an input x and then returns g applied to f applied to x. That's the function that is the composition of g and f that runs both of them. So I could say like, compose, I could even say like, this function, and then also the function. I don't mean to suggest that you always have to say x. It can be any variable you want. So we'll say y times 2. Okay. So this is going to be the function that first multiplies the input by 2, and then adds 1 to that. So like if I call that on 5, I should get 11, because it's first going to do 2 times 5, and then it's going to do that plus 1. Questions so far? Yeah, go on. basically lets me define some variables, and then I say in, and then I get to use the variables. They're kind of local to whatever comes after that. So you could also use that in a function definition. You could say, oh, you know, and you can use this, it doesn't matter whether you're using a lambda to make an anonymous function or whether you're defining a named function. You know, you could just say like, well, what do I want this function to return? Well, first I want to compute, you know, some temporary thing. Like say, okay, let y equal like, you know, 3 times x squared plus 5. And then I want to use y to do, you know, 72 times y. Right. So this might be a way to, well, maybe especially if you're using y like multiple times. It'd be annoying to have to write out that expression for y like multiple times. So the syntax for this definitely looks different than it does in other languages. If you're used to, for example, and again, I'm not assuming that any of you know any particular language. I know some of you have never done any programming. That's fine. And just for those of you that have, I'm making some comparisons now. But you know, like in Python, you could just say, you know, y equals blah, and then, you know, return something with y. So this looks very different, and part of the reason for that is that Python is what's called an imperative language, meaning it's kind of organized around a sequence of instructions, which is do this, change this variable, do this thing, print this. Whereas Disco is what would be called a functional language, where it's not organized around a sequence of instructions, but around defining functions and putting together functions into more complicated functions. So that's one reason for the difference, but you know, you can, yeah. I'll put it here for posterity. You don't really need to know this, but if you want it. Okay, any other questions? Let's do other examples. How about let's make a function called iterate, and here's what it's going to do. It's going to take 3 inputs, or really it's taking 1 input, which is three things together. So it's going to take a natural number, and it's going to take a function, and I don't care what type it is, as long as it's from some type to the same type, right? So it could be like natural numbers to natural numbers, or Boolean to Boolean, or whatever you want. And it's also going to take a value of that same type. So, you know, if the function takes integers as input, then we also need to give it something. And what I want to do is basically like call this function that many times on this, like iterate this function on that input. So, you know, my function, if we call it f, and this is x, I want to say like, you know, f of f of f of f of f of x, some number of times. And the natural number tells us how many times. Okay, so let's do something. So iterate a function on an input a certain number of times. And we can even write some examples, right? So like, for example, iterate 5 times, let's see, how about the function that multiplies its argument by 2? So like lambda n dot n times 2 times 2 times 2 times 5 times, I should get 2 to the 5th, which is 32, right? So this should be equal to 32. Or what's another example? Like, iterate 5 times not on true, I should get false. So if I keep doing not, it's going to flip it from true to false, true to false, true to false. If I do it an odd number of times, I'll get the opposite thing, right? Or, if I say like iterate 0 times, what do you all think? If I do like this same function, the doubling function, and I iterate it 0 times, what do you think I should get? Just 1, right? Because I didn't do the function at all. So I just had that thing I started with. I did nothing to it, so I took that back. Okay, well, let's see if we can write this. So in general, it's going to take a number n, a function which I'll just call f, and some starting value which I'll call s for a starting value. So you might be wondering how we're going to do this. We haven't talked anything about like loops or anything like that. In fact, Disco doesn't have loops. So I'll show you how we're going to do this. Maybe we'll do another one where I'll let you figure it out. But so first of all, we're just going to do this we're going to start by doing this by cases. So depending on what n is, if n is 0, then I definitely know how to do it when n is 0, because then I don't need to call the function at all. So if n is 0, then the answer is just f. Right. And if I wanted, I could replace the f with an underscore just to show that I don't actually care what it is in that case. But, okay. And then otherwise, I'm actually going to put n plus 1 here. Just because I'm basically saying, look, either it's 0 or it's 1 more than something. And if it's 1 more than something, then here's what I can do. I can say, okay, first, let's iterate that function n times. Okay, I want to iterate it n plus 1 times. First, let's iterate it n times, so f of f of f of f of s. And then I just need to call f 1 more time on that. Right? So I need to say f. Okay, so, and in general, anytime you want to do some kind of repetition, this is the way you do it in Disco, is with a recursive function, so a function that calls itself. So notice, right, iterate is defined in terms of itself. And that's totally fine. So you just think, all right, well, what if I did it sort of for a smaller case? What if I did it for a simpler problem? If that gave me the answer, then what's the answer to the original problem? So in this case, the problem is, how do I iterate f n plus 1 times on this thing? So I said, well, what if I could first iterate f n times? Then what do I have to do? Well, all I have to do then would be to call f 1 more time. So this works. So let's see. I never actually, I didn't finish writing the type of iterate. Right now it just says iterate is a triple of 3 things, but I actually want it to be a function that takes that as input and then returns an a. You don't need those parentheses, but I think it makes it a little clearer. Okay. Hey, and look, our test fast. function. And I mean, this is a silly way to write this. I'm just kind of illustrating that, hey, compose takes some functions and returns a function, then we can give that as an argument to some other function. Like, it's totally fine. This is not the simplest way to write this, of course. I could have just said lambda n 2 times n plus 1. But, sorry, I don't know if that's right, but yeah. Okay. Cool. Questions? So this might feel a little brain bending. I don't know, and that's perfectly fine and normal. One thing I will emphasize is that it really comes down to, there's a few kind of foundational concepts that we're just building on top of. So, if you're working on the next homework that's doing stuff like this, and you're getting confused, right? If you just go back and rewatch this lecture, or read some of the documentation about, the foundational concepts are, number one, lambdas. Okay, just understand kind of how those represent a function and how you would use it to write a function. Number two, just the idea that functions themselves are things that you can give as input to a function, or get as output from a function. That's really it. And then beyond that, it's just kind of, then also here we have this idea of defining a function in terms of itself. And we'll do lots more examples of that. But sort of foundational idea. It's really those three ideas that we've introduced. But put together, those are a pretty powerful combination of ideas. Let's do one more example. So, when we first introduced sets in Disco, someone asked, can we represent infinite sets in Disco? And the answer is no. When we say set n, that has to be a finite set. But we kind of can using functions. So, here's the idea. Instead of thinking of a set as like a thing that you can look at and say, here's the elements, what if you imagine a function where you can ask it about any element and it'll tell you true or false, is that in the set? So I want to say something like a subset of the type A is a function. So this, we haven't seen this typing, but this is basically just defining a new type. It's defining just like a name for a type. So I'm just saying, from now on, when I say subset of A, what I mean is a function from A to bool. And we'll think of this as, you can say, hey, how about the number 6? Is the number 6 a member of this subset or not? And we'll say, true, yes it is, or false, no it isn't. Okay. So for example, I could define all n is a subset of n, and I want this to be the one that includes everything, all of the natural numbers. So I can just say, well, that corresponds to the function that no matter what natural number you give it, it says true. Right? Yes, that number is in our set. So if let's see if this. Now I can't print it out, right? Because if I try printing it out, it just says, yeah, it's a function. It doesn't really have any way to print out a function. But I can ask it about specific numbers and be like, well, how about 6? Is that in this set? And it says, yeah, it is there. I say, what about 29? Yeah, it's in there. notice, like, this is kind of representing an infinite set, but the thing that we have to give up is that we can't, like, we can never know if we've, you know, like, I can ask about a few things and find out whether those are in there, but there's always going to be things that I don't know about, because I can't list all the natural numbers and see whether each one is in there or not. Or maybe we could say, like, evens. If I want just a set of all even natural numbers, then that should correspond to the function that takes a natural number and tells us, is it even or not? If it is even, then it's yes, it should be in there, and if it's not even, then it's not. So we could just say, well, we haven't talked about this. We'll talk about this in a few weeks, but don't worry about this. If you don't know what that means, don't worry about it. We'll talk about it. If you do know what that means, then fine. We're basically asking is, if you divide n by 2, is the remainder 0? That's one way to ask it. So if I reload this, I can say, okay, even is is 6 in that set, and it says yes. Is 5 in that set? No. I could even say, like, well, how about all the x's in 1 to 100 or 0 to 100 such that evens x is true, right? And that gives us like the first 100 even numbers. And let's I don't know, I'll call this cube. I could also say things like, I could make a finite subset. I could say, is n an element of 2, 5, 8, 2, 5, 9. Right, so this function only returns true for 2, 5, and 9. For everything else, it returns false. Okay. Now, here's the interesting thing. There's a lot of things that we can do with sets that we can also do with this kind of representation of sets as functions. So, for example, I could write, let's write an intersection function. So I'll just call it subset inter. And it's going to take well, for now, let's just say, like, subset of n. There's a reason I'm not saying A here, because it actually won't work for any possible type A, because it has to be able to make a set out of it. But anyway, we can do it for natural numbers. You can do it for other types too. So how are we going to write this? So I'll say S1 and S2. Okay. And I have to return a subset n. A subset n, of course, is just a function that takes a natural number and tells me true or false. So, and I'm given these two subsets, S1 and S2, and both of them also are really functions, right, that will tell me true or false for a given natural number. So how do I define the intersection of these two sets? I'm going to say, all right, the output is the function that takes a natural number, and how do I decide, true or false, is this number in the intersection of these two sets? Right, what's the definition of intersection? Sure. Right, so the definition of intersection is it has to be in, things that are in both. Right, so it's in S1 and S2. How do I find out if n is an element of S1? Well, I could just, S1 is a function that tells me that. I just apply it to n. And I want it to be in S1 and I want it to be in S2. Okay, so for example, if I say subset inter of evens and q, so the intersection of all the even natural numbers and also q, I guess it's only going to be 2 by itself, right? Because 5 and 9 are not equals. So I can say, is 2 in there? And it says yes. But anything else I ask, it's going to say false. So it's 5 not in there. 6 is not in there. Right. So, and you can write union, you can write difference. You can even write complement, which we weren't able to do with finite sets, but so there's definitely some things we give up, but this is kind of a possible way that we can represent infinite sets, and it, depending on our use case, this might work for us. Right? But it's also just an interesting example of using